in most of the textbooks for pre-grad statistics, and especially the 2-3 that I have referred myself, the standard error of the mean is discussed somewhere after explaining the normal distribution and trying to understand as to how sampling can be done from the normal distribution. Now, firstly, what is required is to understand the standard error of the mean. The standard error in this case does not necessarily mean an error, but it means the standard deviation of the mean from a number of different samples from one particular population. And in most cases that we will find, the population itself will not be necessarily defined for us. So the population size does not necessarily matter, because what we are trying to do is we are from the statistic, which is different from a parameter. So the statistic is of the sample and the parameter is of the population. So from the statistic, which is the standard error of the mean, and various other computations that we will deduce for the sample size, we want to inference certain information, or we want to draw out certain conclusions about the population. And this is thus called the very basic of inferential statistics. So from descriptive statistics, when you move into inferential statistics, so this is considered to be the very basic, the something which is mandatory to be understood. Now I've gone ahead and created certain Excel sheets so that I can display as to what I am basically referring to. And the reason I did this was that I could not find on the internet also many examples done in Excel which explain these particular let's say statistical theories, or the theoretical part of it in a practical manner. So it's a little difficult to follow. So that I can follow this and further display what I have understood. Okay, now what we need to first do is create a random number distribution or a data set out of random numbers. So how is this usually done? In Excel you would probably go and use the random formula. So this RAND over here, all I did was insert the RAND over here and drag it till whatever I wanted to, and then I just created a little a plot over here to show as to what it would look like. This is just playing around with the Excel. What I have actually done is I have gone ahead and used phstat2, and I have created 100 samples of random numbers with sample size 30. So how do you check that these are 100 samples? You look at the count down here, it says 100, which means there are 100 columns with these random numbers. And how do you check that each sample size is size 30? You again check over here. So of course, there is one that says sample mean. So ignoring that, there are 30 random numbers within this particular column. So any column has got 30 random numbers. Now, once this is done, what you need to do next is you need to find the mean for each and every column. So the mean for each and every column, of course, is the average for each and every column. And you see down here that we've gone ahead and, or rather this is done by phstat, the program itself, the software itself, so the add-in itself. So I have not done anything over here. So you go ahead and create this, and you have the average of each and every column. So you've gone ahead and done that for 100 columns. Now once you have the sample mean, so these are your samples, and you have the means of these sample, you further want to have a mean of these 100 sample means, right? So this is the overall average. So this is the overall average, and further onto this you want to have the standard error of the mean, which is nothing but the standard deviation. So you can very clearly see over here that Excel has, rather phstat2 has gone ahead and populated this sheet with a formula in A38, which is basically standard deviation of the entire row 34, right? So simply put, it is just a standard error is nothing but the standard deviation of all the means. Now, having looked at this, what is the central limit theorem, or what is the next inference that we want to draw? So the central limit theorem clearly states that once you have taken a sample of, once you have taken a mean of a number of samples, whether the population or the samples are normally distributed or not. So whether these random numbers are normally distributed or not, the samples of the means would be normally distributed. Now let's see how that happens. So we've also gone ahead and chosen the histogram option, and this looks like a histogram which is kind of normally distributed, because you have certain tailing values and you have the peak right in the middle, whereas 0.6, but it does not give you a very clear picture. So what you could think is, also I really don't know if this really works. I am not necessarily sure, but let's look at another example. So in this particular example that I've shown you earlier, I have taken 100 samples of size 30 each. So the n being 30 and the number of samples taken is 100. So the n is not 100 over here. The small n, which denotes the sample size, is 30. And then you look at this other sheet that I have over here. Over here, the small n is 10, and the number of samples I have taken is 1000. So if you were to look at this particular row, you count this particular row, you have 1000 entries of random numbers in this particular row. And over here, you can see that the sample size, the n, is 10. And this is true for all the cells that I have. For all the columns that I have. And I have till column 8LL on this particular sheet. Again, the same thing, you go ahead and take means for each and every column. And then you take the overall mean, which is the overall average for this particular row, which is row 14. And then you take the standard deviation for this row 14, which is nothing but the standard error of the mean. And once this is done, again a histogram is plotted, and that histogram looks like this. Now look at this difference. Now, does this histogram look little bit like a normal distribution if you were also to plot say a frequency polygon, or if this histogram also had a linear graph over here, which is a polygon plotted on top of it, the way I'm moving my mouse right now, then of course you might say this is more like a normal distribution than the one that we saw over here. Now let me look at another data set. The third data set that I am going to show to you is 10,000 samples of 5 each. So the n over here is 5, and the number of samples that I have is 10,000. So if you count this, it is straight away showing you count as 10,000. Let me go down to the last column and see. So I have gone up to column NTP, right? And I have again gone ahead and taken the mean for each and every particular column, and we have gone ahead and taken the mean for the entire row number 9 over here, and we also have taken the standard deviation for the row 9, which is again the standard error of the mean. Now let's look at the histogram that we got from this particular data set. The histogram that we got from this particular data set is this. Now anybody can look at this histogram and say, yes, this is definitely a normal distribution. Whereas our data set itself might not be normally distributed. These might not be normally distributed. The column G or the column H, or our samples might not be normally distributed. Our data set also, the entire population which is might not, from which we've taken these samples, might or might not be normally distributed. But what is normally distributed is the means. So this bin is made up of the means, right? The means that we are getting over here in row 9. The sample means, the means of these samples, the 10,000 samples that we have taken, are plotted over here in row 9, and once you create a histogram out of these, you can see that the histogram has a normal distribution. So this is as far as the normal distribution and the theoretical part of this goes. Now how do you go ahead and practically implement some of this? Okay, now let's look at a different example. Presume you have a population size, whatever that population size is, we are not necessarily bothered right now, but you have a sample size which is 100. And the sample mean, which is the x bar, and this is not the mu, so the mu is the population mean and the sample mean is the x bar. The sample mean is 365, say 365 days in a year, so whatever, and the population mean is 368. And what is also given to us is the standard deviation of the population, which is the sigma value. And now from this we've gone ahead and we've calculated the standard error of the mean, again just like we did in the other examples that I had shown you, but there we actually had the data set in front of us. Over here we don't have the data set. The only thing we've been told is that there's a sample mean and there is a sample, so there's a population mean, and then there is a standard deviation of that particular population, which is sigma, and of course the sample size is given to us. So from the sample size and the standard deviation of the population, which is sigma, we've gone ahead and derived the standard error of the mean, or the standard deviation of the standard deviation of the sample, this particular sample, or these 100 samples, and which is nothing but the standard deviation of the population sigma divided by the square root of the sample size, which over here is 100, and we've got 1.5 as the answer. Now this is our x scale, and in the standardized normal distribution, which I had done the video earlier also, and of course that is something which most of you might be aware of, there is a parallel scale which is there, which is the z scale. So you have to convert the x values to the standardized z scale. So even if that particular x scale is not a normal distribution, the z scale becomes a standardized normal distribution. So how do you do that? You use the formula standardize in Excel. And what does this formula basically do? It takes into consideration the sample mean, which is the x bar, the population mean, which is the mu, and the standard error of the mean, which is sigma x bar. So you can see the formula over here. And now what we basically want to understand is, under the z curve, under the curve of the z scale, what is the area which is there under the standard normal curve? So how do you find that out? Is again through the norm.dist formula in Excel, and this is in Excel 2010. In Excel 2007 it is norm.dist, which is a continuous word. Okay, and so we've gone ahead and considered this norm.dist, and again getting the sample mean x bar, the population mean mu, and the standard error of the mean, which is sigma x bar. And for cumulative, yes, true, because we are looking at all of the data points below, that is from 0 till -2 on the z-axis. Oh, sorry, not 0, but the lowest value of the z-axis, which could be say -6. I'm just taking a guess over here. I don't know what in this particular data set as to what would be the lowest value of z. So whatever that value is, from there till -2, what will be the area under the curve? And then this gets converted into a percentage. So that is a cumulative distribution function, and the cumulative distribution function shows that 2.28% of all of values on the z scale would lie below this particular point, that is -2.00. Right? Okay, now looking at the next example. Say again, the population size is not given to us. The sample size given is 25. The population mean. So they've not given the population size, but they've given the population mean, which is 368, and the standard deviation of the population being the same. So this is the same population out of which a different sample size has now been taken. Earlier the sample size was 100, now the sample size is 25. So if you look at these two over here, the sample size has changed, rest of the data set is the same. And now there is a certain percentage question. So they're saying 95% of values would lie below what value of X? Right? So that is what the question is. So what we'll go ahead and do is we'll input all these over here. So 25, 368, 15 and 95%. This is what has been given to us. What we need to get is the lower value of Z and the upper value of Z, and then convert from these to the lower value of X bar and upper value of X bar. Now this is similar to when we say X bar, it's almost similar to the X scale. So you need not confuse between because it is the mean of certain samples, it is still behaving in a manner which is in which the X scale would behave, which is just the mean of certain numbers and not necessarily samples. And why do we use the norm S dot inverse over here? And what is the logic of that? So under the curve, which is the Z curve or the X curve, the probability is defined between 0 and 1, which is 0% to 100%, and then there are no values beyond 100%, and their values cannot go below 0%. So if they say that 95% of the values fall under what particular range, and this is normally distributed, that particular term I am forgetting, just let me see if I can find that now. But normally distributed across the mean. No, not across the mean, but on both sides of the mean or something to that effect. So basically what happens is, for the Z scale, the mean is at 0. Right? The mean and the median for the Z scale is at 0. So once we go on both sides of the scale, it is normally equally distributed. So 50% values lie above and 50% values lie below. So if we were to look at 95, then so by this formula, so if you were to reduce 95 out of 100, you get 5%, and then you of course have to break that 5% into two different values, divide that by 2. So one value 2.5% will be the top the top edge of the Z scale, and the other one will be lower edge of the Z scale. So where the Z scale tapers down and meets the x-axis, that is where these values will lie. So that's the reason we've gone ahead and used this particular formula, which says 1 minus C17. So what is C17 is nothing but 95% divided by 2. So that normality is being inversed. And like the formula itself shows over here, it's the probability value, which is 95%, that we want to input over there. So how do you find the upper Z value? Of course, you just go ahead and look at the absolute value and the positive value over there. Now the sample mean, which is the X bar over here, we are not necessarily concerned with. That has not been asked of us, and we are not necessarily giving that particular value. We are looking at a range. We are saying the lower X bar value and the upper X bar value. So we are not looking at one particular number, but we are looking at a range over here. And how do we derive that range? This is the formula for it, which is population mean plus the lower Z value multiplied by the standard error of the mean. Now how do we get the standard error of the mean over here? You get the standard error of the mean by again inputting the same formula which was used earlier, which is the sample size, which is the mean of the particular population, which is sigma. Sorry, standard deviation of the particular population. No, one second. What is C15? population mean, which is mu, divided by the square root of the population size, which is square root of 25 in this particular case. So the formula remains the same, and you've also factored in the population mean and the lower z value. And to find the upper x bar value, you will go ahead and factor in the upper z value. So from the z scale, you are deriving the x scale basically. So that is what is being done over here. Now look at the next example. Again, the population size has not been given. The sample size over here is 100, like it was in the initial example. The sample mean, which is x bar, has been given to us, which is say 47. The population mean is there, and let me read out how this question actually has been posed. So given a normal distribution, so we are told that it's a normal distribution with mu is equal to 50, which is the population mean equal to 50, and the standard deviation of the population equal to 5. If we were to select a sample of n is equal to 100, so this is the sample size, which is 100. It is not 100 samples. Sorry, I think I said 100 samples earlier. What is the probability that x bar is less than 47? So we are looking at the probability of x bar, which is the sample mean for this 100 sample size, and we are looking at the probability that what is the probability of this being less than 47. So it does not say less than or equal to, it just says less than 47. So we go ahead and calculate the standard error of the mean, which is not necessarily required, but going ahead and doing it any which ways. The z value that we get is minus 6.00. So the moment you get this z value, immediately you should have an alert saying that this is the lowermost value possible on the z scale. And if this is the lowermost value possible on the z scale, then the probability of anything being lower than this is 0. So the probability will range between 0 and 1. So even if it was 0.001, then we would say it's a positive probability. There is some probability of such a thing happening, but because it's gone to the absolute 0, so I've gone ahead and gone to, I think, around 6-7 decimal places over here, and further also there's hardly anything I get till the 9th or 10th decimal place over here. So we can safely say that the probability of such a thing is definitely 0%. Right? And again, the formula is being used. How did I get the z value is again with standardize. How did I get the probability of the x being less than 47? I got it by the norm.dist function. Again, in 2007, it would be norm.dist, continuous one word. Now further, in this particular question, they wanted to understand as to what is the probability of getting values for x bar less than 47. But presume we had a range. Presume we said that what is the probability of getting something between 47 and say 50, or what is the probability of getting something between 50 plus or 47 less than, something to that effect. So this is how you calculate the range. So these values remain the same. The sample size is 100. The population mean is mu, which is 50. The standard deviation of the population sigma is 5. Now, so the sample mean x bar, the value 1 is 47. There's another value given to us, which is 49.5. Another value given to us, 51.1. And then there's a cumulative percentage. Just like this over here, 95%. There's a cumulative percentage which is there. So now for all of these, we are supposed to go ahead and derive the z scale and the x scale. So this is how it is done. Again, for the z scale, you standardize and you get different values for the z scale. As is intuitive over here, 47 being the lowermost. If you were to look at 49.5, it will be a little higher than this. So it's gone to, so which means the values are quite tightly packed over here, and 51 is again gone on the positive side on the Z scale. And now the area below 47 is 0% that we've seen in the example above also, and the area above 49.5 is basically 1 minus the probability of these two, right? Okay, and then the probability of something being less than 47 or being more than 49.5 would be actually the sum of these two probabilities, which will again be 84%, because anything being less than 47 is not possible in this particular example. And the interesting bit is what will be the values which will lie between 49.5 and 47, or what will lie above 51. So what will lie above 51, again this is how we'll get that value. So this is how we go ahead and practically use some of the learning from the earlier examples which I showed you over here. So whenever we talk about the standard error of the mean, it is not necessarily just to go ahead and display the central limit theorem, which of course you can display. These are certain practical examples of this. Now again, looking at so let's say we have a sample size of say 100. Yeah, okay. This is another way of looking at this. Now, as the sample size increases over a period of different samples, the standard error of the mean will also increase, right? But again, this is something which is a little experimental. I think I need to get back to this later. Thanks.